When I was a kid in Southern California, my brother and I would spend our summers throwing ourselves into the ocean and attempting to learn how to body surf without drowning. Every so often, you'd get crashed to the bottom by a big wave, and you'd hold your breath and hope that you'd somehow find the sky again. After that, you'd crawl onto the shore and lie in the hot sand, basking in the warmth of the sun and the sand. Perhaps you grew up in an area with a cold river or lake, and you'd come out and you'd lie on a hot rock. You ever think about how the sand of the rock absorbs the sun's energy and retains it and then releases it? We learn so much from observing nature and understanding how things as simple as heating up a rock or a bed of sand can translate into practical applications for humanity. Today we're talking to CEO and founder of Rondo Energy, John O'Donnell. His company is taking technology that has existed for over 3,000 years and putting a new spin on it. He's introducing AI to hot bricks, a thermal battery that can store hundreds of megawatts of renewable power and turn it into industrial heat. This is key and important because 25% of the energy consumed on this planet goes into the production of heat to make things like ketchup and baby food and chemicals and steel and concrete, or so many other things that you've never really thought about. It's a big chunk of our energy consumption, and they're really hard to decarbonize. But John and his team have a solution to make this happen. I'm Jim McNeil, and this is Good Clean Energy. John O'Donnell, welcome to Good Clean Energy.
Thank you. It's a pleasure to be with you.
I'm really looking forward to this conversation because it seems like you and I have kind of similar backgrounds. We both started out in the software game and in the dawn of the microprocessor, if you will, and somehow found our way to energy. Tell me a little bit about, your origin story.
Yeah, actually, I was originally a computer scientist, and right out of college, my first job was at Princeton Plasma Physics in the tokamak fusion program, building real-time computer systems. A couple of years after that, I wound up starting a supercomputer manufacturing company, and that turned into a semiconductor company that was building the highest performance image processing things. So I wound up with a couple of machines in the Computer History Museum that makes me a dinosaur, I think. My boss's boss from way back is a senior guy on ITER. But 2005, I sold the chip company and was deeply interested in energy. And are we at a moment where we can create the conditions for giant flows of private capital building new clean energy infrastructure by any means necessary, because that's what Earth needs the most? I fell in love with the solar thermal space as an area that it looked like you could create those conditions. Market-priced energy from clean sources, central large generation playing important roles for utilities. Bought a company, built a company, sold it to the French nuclear giant Areva, wound up briefly being a partner in a boutique venture fund looking at carbon removal because I was skeptical that we will see the conditions where an infrastructure the size of the world petroleum industry is created for carbon removal with no real revenue model. Is that going to happen in a relevant time frame? I'm skeptical.
Good question.
I wound up meeting the founders of another solar thermal company that were specifically focused on solving industrial heat. We wound up building more than half of all the solar industrial heat that's running in the world. But calling that a drop in the bucket is overemphasizing the size of a drop.
Yeah, let's wait a second before we get into that. I just want to comment on your time at Princeton Physics Laboratory, plasma physics, actually.
Yeah.
I think in the venture community, one of my favorite quotes is another word for being early is being wrong. and I think when you were there, there's a time frame when they were kind of messing around with deuterium and tritium and doing experiments, right?
Oh, indeed, as they still are.
Yeah. Well, that particular reactor, I think, has been mothballed because it's radioactive. But
yep.
It kind of brings up the challenges of, what do we have to do to make fusion work? And I'm on the side of the camp that believes that we're not too far away from proving net energy out. I just don't think we're going to do it the way Princeton was trying to do it back in the 80s and the 90s.
I hope you're right. It would be phenomenal. Yes.
In the meantime, you have focused your energy on the energy sector, and in particular, the challenge of industrial heat. I think everyone thinks that an industrial facility is plugged into the grid just like we are, and maybe we boil water or we run an oven or we run a conveyor belt. But that may not be the case. I mean, what is the role of heat in industrial processes?
Yeah, heat is how we make almost everything, whether it's cooking baby food or sterilizing containers or making glass or aluminum or steel, chemicals. And you look at a production facility and it's not necessarily obvious, but the vast majority of the energy that they're consuming is in the form of heat. And that's in boilers that are making steam that's going around the plant, or in other industrial facilities, it's in furnaces that are heating glass or melting metal to be cast. People have thought of industrial heat as the hard to decarbonize sector. It's principally an economics matter for lots of industries. The cost of energy is a huge portion of the total cost of production. People are selling low price, non-branded commodities. The energy supply, if it's going to be decarbonized, it has to be low cost. It has to be not raising the cost of production. Industry needs energy supplies that are continuous. Facilities get shut down once a year, and even brief interruptions in energy supply can cause process trips. Worldwide, 3/4 of the energy consumed by industry is in the form of heat, not electricity. It's fully 20 to 25% of total world final energy use and 1/4 of world CO2 emissions.
It's a big slice of the production in the carbon pie.
Yes.
And to understand what heat is used for, it's used to make food, concrete, chemicals. Why don't you break down how heat's applied?
Yeah. So in the United States, the single largest sector of industrial heat is actually refining fuels. Next is chemicals. Next is making paper. Next is making metal products, then food. Now we get to iron and steel, and then cement, then wood products, including non-paper products, and then smaller things, glass and aluminum are the sort of the last two in the United States.
Yeah.
That mix is a little different, more globally. Steel and cement come up.
You're not going to get a bottle of ketchup without industrial heat.
Yes, making both the bottle and the contents. Yes.
Yeah. Okay. So, like you said, it's 25% of global consumption, such a huge number. And this heat is produced using coal and natural gas typically?
Almost everywhere. It's again, what is the lowest cost fuel? Natural gas and oil are actually the big two. Coal in some of the larger facilities, yes. Mm-hmm. And depends on where we are in the world, right? The mix is very different in China, where there's more coal heavy. Europe, the United States is much more natural gas heavy. Yeah.
So now we're at this inflection point where renewable energy on a cost per watt basis is less expensive than coal or gas, right?
On a cost per kilowatt hour, per watt hour basis.
Yeah.
And that's something that's just happened, right? Renewable electricity got cheaper than electricity per kilowatt hour, but it's just now crossing where it's cheaper than just burning fuel per kilowatt hour.
So when you talk about these industrial processes, how much of their cost is associated with energy?
It depends very strongly on the commodity. With cement, it's 60% or something, the cost. With food, it can be in the 15 to 20. It varies very strongly by commodity and by where we are. That is, what is the price of fuel? We see the chemical industry in particular chasing where is fuel low cost. A friend said, why was all the 19th century energy in the UK on the coast? That was where it was cheap to bring the coal. We've seen huge disinvestment and reinvestment in the chemical industry in the United States associated with high gas prices in the past, and then what happened because of shale gas. We've seen thousands and thousands of people laid off in the chemical industry in Europe just because of Putin's war and the impact in gas price and availability.
Oh, that's interesting.
So there are energy intense industries, but then there are energy sensitive industries that are so, but it varies a lot.
Yeah, it's the old maxim, hey, Willie Horton, why are you robbing banks, right? Because that's where the money is.
Yes.
But you're saying, they're going to where there's cheap energy because energy makes up a substantial part of their cost of goods. And in low margin businesses, that's the difference between profit and loss, right?
That's right.
Yeah.
And in today's world, because of the urgency of decarbonization, low cost renewable energy or low cost clean energy, shall we say, actually drives long-term economic growth that's beyond the energy sector itself. That is, people are looking at where are we going to put future data centers, future chemical factories, future all kinds of things based on the near-term and longer-term availability of clean, low-cost energy in those places.
So you're in the business of storing energy, and we're talking about the low cost of renewables. So if I'm a chemical plant, why don't I just put a big wind farm or a solar array in my backyard and just go directly to that?
Well, that's part of the answer. And of course, for your electricity load, that works just fine because you'll interconnect that wind farm or the solar array and you'll lean on the electricity grid to absorb all the variability and to give you a dead reliable, continuous supply of energy for your facility. The grid is excellent at instant response to varying load demand. It's a very different matter if I want to supply 3/4 of the energy that I use, which is heat. I can't just put in an electric furnace or an electric boiler or something and run it off that because yes, in principle, I could balance renewables with fuel, but not with industrial boilers, not with industrial furnace. They can't adjust as fast as renewables change. And the other matter is you're only going to get 30% of your annual energy from that behind the meter thing. But if you had low cost storage, you could build a large enough wind farm, a large enough solar facility to deliver all of your annual energy and to do it continuously with exactly the same process conditions as you're running today.
So to be clear, renewables are less expensive forms of electricity. If you put storage on site, you can take your excess energy you're not using at the time and you can store it away in the form of heat. And since you're focusing on industrial processes, the output is supposed to be heat. And so what's the efficiency of your storage and how much am I losing by taking electricity and putting it into heat and then using that heat?
Yeah. The efficiency of electrochemical storage, the efficiency of hydrogen systems. We're doing electrochemistry and there are efficiency losses that are in the form of heat. That is, there's, unwanted heating up of the battery as it's charging and discharging, et cetera.
When your electrochemical battery heats up, that's not a good thing. That means you're losing energy.
It's not a good thing.
Yeah.
That's right. But your toaster takes electricity and turns it into heat at 100% efficiency. Or there are no losses in your toaster except, through the outside shell of the toaster. Similarly, electric thermal energy storage, we have heaters inside that are just like the heaters in your toaster. There is no loss in turning electricity to heat. And because of a technology called dynamic insulation, the system loses about 1.5% of the energy that's input. 100 kilowatt hours of electricity in is 98 kilowatt hours, 98.5 of continuous heat out as steam or superheated air. It happens to be the world's most efficient way of storing energy.
It's pretty exciting. The thing that's really fun about what you're doing, John, is it's ancient technology. I mean, if you go back to the Roman Hippocaust, right? you go back to the Roman baths, and what they were doing is they built their facilities on columns of bricks over airspace, and then they would heat up that airspace, and those bricks would store all of that heat and release it over time. It was the early days of radiant heat, right?
Thank you. That's exactly right. We started with, in the 1820s, the steel industry started building these things called blast stoves or cowper stoves that have thousands of tons of brick that stores heat that's captured from the exhaust from the furnace and then delivers it as preheat to the inlet of the furnace. And we're using exactly that brick and exactly those physical principles with a physics insight about how to heat it with electricity instead. We had not really gone back to the Roman baths, but thank you. We are actually using what the steel industry used for 200 years, but
Yeah.
they looked back to Rome. Yes.
When you start building on a lower scale, you can put one in my property and I can like heat up my pool and my hot tub.
Well, indeed. And, there are these residential things called storage heaters that were popular in places like the advent of nuclear plants in the UK in particular. Storage heaters that heated brick with intermittent electricity were a great way absorbing variability and capturing low-cost nuclear power at night to deliver heat on demand.
Yeah.
And it's again, those same materials and principles.
And that's effectively what's happening here. So you're taking electric filaments that are distributed through, a box, if you will, that has columns and columns of bricks with air space between them. I mean, what does that look like?
Yeah. So the basic unit is, I think, a 10 by 30 meter footprint. It's about 6 meters high. And there's a 3D checkerboard of brick and open chambers within a brick array. And there are air passages that let air flow vertically within that array and open passages that let thermal radiation move horizontally. So there's 1,500 tons of brick, stores about 330 megawatt hours of energy. And if you looked at it from the side, on about a 1 meter spacing, you would see electrical heating elements that run through, they're 8 meters long, they run through the array. And each of those is on the order of 300 kilowatts. So all in, it's 70 to 100 megawatts of input electricity that's being distributed, heating this 1,500 ton array of brick when power is available. And energy is continuously delivered when it's wanted by circulating cool air in through the bottom of that brick array, getting air out that's at over 1,000 C, and then mixing its temperature down so that we can put it across conventional boilers to make any condition of industrial steam, or taking that superheated air directly to a cement kiln or an ethylene cracker or something like that. It's a very boring box looking at it from the outside, but that's what's inside.
It's pretty amazing. So your total box is 300 megawatts, you said?
Yeah, it stores a little over 300 megawatt hours. It delivers 480 megawatt hours a day. And it's a one-for-one replacement with a common size of industrial boiler, of which there happen to be more than 300 here in California and many, many thousands around the world.
And to deliver that heat, do you run a fan and blow the air out, or is there water? Is there a heat exchange? How does that work?
So a huge portion of the steam in the world comes from what they call HRSGs, HRSGs, heat recovery steam generators. A combined cycle power plant has a jet engine. The exhaust gas from the jet engine flows across a set of boiler tubes, the HRSG, that raises steam. And then the combined cycle power plant, it drives a steam turbine. Or in other cases, you use that steam for an industrial process. We engineered these heat batteries to use those same boilers. The exhaust from a jet engine is around 605 degrees Celsius. We put air out at about 650 into those same boilers and do that entirely within the box. So unlike the jet engine powered boiler that has an exhaust stack, the return air coming out of that, the exhaust air from the boiler, circulates back inside the box, so there's no heat lost, which is why it's so efficient. But we take a conventional boiler.
So you're replacing a jet engine with a box of rocks.
Fair enough. Yes, that's right. And no combustion.
And obviously some control systems. And then are you running a fan?
That's right. Internally, there's a blower that's moving air through that. And, we have guys in the team who do computational fluid dynamics. One of our guys used to do hypersonic vehicles. Other guys did Formula One race cars. Here they do computational fluid dynamics for air that's moving at 2 miles an hour.
Amazing.
Inside the box. Yeah.
But that's the fun stuff. I mean, because you basically took some of the oldest heat storage technology known to man, which is hot rocks, and you've applied modern technology in terms of the control systems you're using to put out the temperatures you need at the duration required.
Yes. And the other modern technology that was critical was the computational infrastructure to do the multi-physics simulation to get this right. Because it's easy to describe it, but There were 74 design revisions that led to the aha. Oh, this is easy now that we've had the aha. But yes, exactly right. The modern control systems are also critical. Where are we putting power into the unit? We're running a computational model of the unit as it's in operation so as to guide where we put power inside it.
And I imagine on a cost per megawatt or kilowatt, whatever you're measuring with, is probably less than what it costs to buy a jet engine, right?
Yeah, but more important, it's a fraction of the cost of any electrochemical battery, any hydrogen electrolyzer system. And hydrogen for heat has been one of the, that's going to be our answer. And it works, but it's 48 to 52% efficient. These things at 98% efficiency, save twice as much fuel per megawatt hour of electricity.
Yeah, I think since hydrogen is super portable, it's probably got much better applications in transportation and other things. Whereas if you're sitting next to a local solar or wind farm and your output is heat, that's what you want. It seems like it's a no-brainer, right?
Yeah, hydrogen does play a role when we look at, on an annual basis, a solar array in California will give you twice as many megawatt hours on a day in July as it does in January. So we are seeing in these models that the International Energy Agency and academics are running, we're seeing models that say the cheapest fully renewable thing is like 30% hydrogen because some energy is being moved from July to January, or filling in those periods the Germans call the Dunkelflaute, the dark doldrums when the wind isn't blowing and the sun isn't shining.
It's a wonderful word.
But this technology that's really designed for storing energy for a few days, these are technologies that work really well for 1 to 7 days. They're going to supply 70 to 80% of the annual energy. And that seems to be true in any place where there's a bunch of renewable penetration in the grid. Right. In some cases, in fact, these things are going to be absorbing what would otherwise be low or negative price power from electricity grids. And that's clean power coming from a reactor someplace. They are bringing up the floor and levelizing electricity prices and stabilizing the grid, because people talk about things like electric vehicles playing a role as flexible loads in the grid. But they're diffuse, they're not centrally controlled. We are serving this completely new application for electricity, and we're electrifying industry without adding stress to the grid. And we've got these loads now that are instantly dispatchable so they can benefit the grid. We've learned a ton in discussing with the utilities and looking forward at their future transmission and distribution build-out plans. One of them said, look, our energy policies today go back to Thomas Edison, where every megawatt of load meant a megawatt of transmission and a megawatt of spinning metal. And every megawatt hour was a couple of megawatt hours of burning fuel.
One of the things we discussed on the show is we talked to professionals about what's involved in getting renewables connected to the grid, and it's non-trivial. It's a big challenge. There's a lot of obstacles and roadblocks that are being put up by different parties, including utilities. The fact that you can build a 500 megawatt wind farm in Oklahoma doesn't mean you're going to get it to the grid and you're going to make money. And you talk about industrial processes and chemical processes, following cheap energy. It seems to me that it would be likely that these kind of organizations would want to reposition themselves next to either good wind areas or good sun areas and not have to depend on the grid because they have the ability to store this energy and use it 24/7, right?
Absolutely. The interconnection time for a new solar project on average in California is 7.5 years. A new wind farm connecting in the UK apparently is 15. The East Coast PJM is not even taking applications, and apparently there's 2,000 gigawatts of proposed renewable energy projects that are in the queue waiting for grid connections. You said it right. If we've got an industrial facility, being able to build private generation that doesn't need a grid connection, we can build 700 megawatt, 1,000 megawatt class generation that fully repower a refinery or a chemical plant, or 150 megawatt things that repower a food producer that don't need grid connection. There's this opportunity to go much faster in total renewable deployment and to make money and provide a lower cost source of energy to that industrial today and not 10 or 15 years from now waiting for the grid.
Yeah, that's what's exciting about what you're doing because you've already installed product. You got product shipped and working, right?
Yes, we are running a first unit at an ethanol refinery here in California that's been running for a while now and is the place where we're studying reliability. We're building and developing projects across a lot of sectors, from other fuel producers to we have chocolate and whiskey and paper and a variety of chemicals. And I just recently, we announced a round of financing that was jointly led by Rio Tinto, one of the world's largest mining companies, Microsoft, Aramco, SABIC, the world's largest chemical company, some cement manufacturers, and climate investors, our original ones, and John Doerr. This is a cross-cutting technology that delivers economical clean energy across many different applications. As a small company, one of our challenges is focus, but we're engaged in a number of sectors today.
Yeah, but you're not limited by access to cobalt or lithium or copper. You're using clay.
Yes, dirt, clay, yes. Silicon, oxygen, and aluminum. 80% of Earth's crust make up 99% of what's in a brick, or 98. There's a little calcium as well in the binder. Humans have known how to make brick from clay for a long time. And there are no critical materials. And the heating elements are iron with a little bit of chromium and aluminum. So
right, what you'll find in your electric oven, basically.
Yes, that's right.
And the enclosure, you talk about dynamic insulation. What does that mean?
So I mentioned that I described this process where the way you pull heat out of the system is you push cool air in at the bottom of the stack, you get superheated air out at the top. That flows through a boiler, which pulls the heat out of the air. The core stack is surrounded by high temperature insulation and a flowing blanket of that return air. So any heat that leaks out of through the primary insulation just warms up that return air. So then there's an outer box, which sees the same temperatures as your home oven, like 150, 200 C, not 1,000 or 1,500. So the dynamic insulation is that flowing gas is absorbing the heat leaking through the primary insulation and then returning it into the process, which is why the system is as efficient as it is and why the outer box is completely cheap conventional material.
So you can produce supercritical heat, which is used in a lot of food processing and
that's right,
chemical processes. And these are temperatures in excess of 500 C?
Yeah. We serve about 95% of the total heat used by industry worldwide. With the one notable exception, when you make cement, there's kind of a two-step thing. The first step they call calcining, where you take limestone rock and you boil the CO2 out of the rock. It turns into calcium oxide, to lime. Then you take that and you put it in a kiln with silica and they make what's called clinker.
Yeah.
Yeah, that step, the clinker step, is at around 2,000, 2,200 C.
Okay. And I think it's important to note that you're going after the industrial heat application, which doesn't really require for you to spend a lot of time comparing your storage mechanism against, hydro storage or flow batteries or compressed air. You want to touch on some of those technologies and why they're not directly competitive with you?
Well, in principle, you could use any of those things, and it's principally, it's a matter of availability and cost. That is, pumped hydro is a phenomenally cost-effective way of storing electricity in the places where you can do it. The world's a little short on places that we can do that.
Yeah, basically it means you need to have a lake above your building is what you need.
Indeed, up a ways. That's right.
You need to be able to pump water up, to a distance so that you can drop it down again and spin a turbine, right?
Yeah. And it's not bad. It's 75, 82% efficient, something like that. Very low cost, long-term storage. All those things are great. It's just, where are you that you can do that? You need to get it permitted. It's just a simple matter of economics. Avoiding electrochemistry is just... There's nothing cheaper that I know of turning electricity into something else than the wire in your toaster, the wire in your hairdryer. We have a fundamentally lower cost. We do not have an electrochemical cell or an electrochemical membrane. So it's just a matter of cost.
So really the big business is going to be how many can you make? Are you going to focus on one particular industry versus another? Or are you potentially the replacement for a furnace that's currently in place? I mean, that's kind of what it feels like.
That's right. I think, but again, back to that seasonal variation thing that I mentioned, most places we are sitting next to an existing boiler, next to an existing furnace. And, you're going to run that furnace a couple of hundred hours a year, that boiler a couple of hundred hours a year. And because we have modern grid and weather forecasting, we're going to be able to tell you a day ahead, tomorrow you're going to want to turn the boiler on because we're going to run like this. So it's a drop-in, very simple solution that when we were thinking about how we were going to do this, one of the core principles was, if you want to go fast, it better be simple and boring, but it better not require the factory owner to make changes to the process, because factories get replaced on decades timescales, not years timescales. All the electrical, all the boiler stuff that we do is reusing the stuff that industry uses today. We really do use the same boiler manufacturers and designs as the jet engine ones.
Yeah.
And we focused on, building the right manufacturing partnerships. Just recently, we announced with our manufacturing partner in Asia, we have 2 gigawatt hours of manufacturing capacity running right now that will grow to 90 gigawatt hours a year in just the next few years. So that's larger than any battery factory in the world today. And it is embarrassingly cheap to do that. Brick kilns don't cost much to build. This is a very simple manufacturing process. And because it's got positive economics right now, these can be early points on the scoreboard in the big decarbonization game. It's something that can be done quickly and simply. It's not terribly sexy. One of the greatest compliments that we get given is a little boring, but I guess a lot of good ideas are like that once you have the insight.
John, you're the purveyor of bricks. Come on, how boring can you be? I mean, really?
Well, I built supercomputers. I worked on supporting people doing tokamak research. I built semiconductors, and
that was the easy stuff. Now you're changing the world.
There is one perspective, as you say, Roman baths. Like this is the lowest tech thing, but by far this is the highest impact thing. If you look at the IEA and the other studies, 70% of industrial heat, if we and others like this class of electric thermal storage, is the least cost solution for 70% of industrial heat. Transforming that is 15% of world CO2. And we see a clear path. We have a clear path to get that done in about 15 years. There are no material or systems or economic obstacles to doing that. It's on us. And we're in the early part of that game, but we can see that this can have a very big impact. It's rate limited by how fast we can build that 8,000 gigawatts of new wind and solar. We see that about 40% of those gigawatts, when we look at Europe and the United States, at least 40% of those gigawatts can be built without any grid connection based on that local idea.
Yeah, you get to skip the bureaucracy of connecting to the grid because you have a big enough industrial process to warrant its own renewable energy production.
Yeah, exactly. And skipping that is critical to getting this done fast. And the other 50%, 60% over the coming 10, 15 years, yes, everybody knows we need to be building grid 3 to 5 times faster than we're building it. But the great issue is the first half of getting this job done doesn't need to wait for that. It can be going on concurrently with it.
Yeah. So what do you think the world looks like in 2035 in terms of how many thermal batteries are out there? And of course, you have to take into consideration that you're going to have unlimited amounts of carbon-free fusion power to push power into your bricks. What do you think the world looks like?
The faster you can make that thing happen, right? That's phenomenal. And in that world where we have those fusion reactors, just like a wind farm, have next to zero marginal operating cost. But unlike a wind farm, they can operate continuously. So operating those things base load is a super important thing for their economics, of course. And as I mentioned, the 2,000 hours of negative electricity prices last year in Oklahoma, everywhere in the world, we are going to see, by the time those fusion reactors are coming online, tons and tons of wind and solar in the grid. Technologies like this play an enormous role in absorbing that generation, absorbing that variability so that new clean power can run base load and can be profitable running base load. So we think there's a really important synergy. By 2035. It's about 128,000 of our standard unit to repower all the furnaces and boilers that are in the world now.
Okay.
Now, the industrial sector is growing, and it needs to grow as the world gets richer. But, give or take, we've done half of that, something like that. But again, the thing that we look at is, have we created the conditions for giant flows of private capital to build big clean energy infrastructure? The availability of working fusion technologies is clearly one of those things. This is also one of those things. We're unlocking the ability to build big and do it now. But again, we see 2 years ago, Sweden turned down 80% of the onshore wind farms that were proposed. We're in a race for our lives, for our children's lives, and we're running that race with shackles on our feet. Some of those shackle matters of permitting large renewable projects and, for that matter, other clean generation. We need policy work to address some of those things. That's one of the biggest things. When I look at 2035, that's the biggest matter, is those policy things.
Yeah, John, I think the good news about what you're doing is that it appears to be an intelligent economic move for an industrial company to use cheap renewables and store it, in your brick furnace. It's going to reduce their operating costs. It's going to give them bragging rights because they're going to be doing carbon-free production, and it's going to save them money.
Thank you. That's a great, simple summary. Thank you. Yes.
So the thing that I think both you and I know is that there are technologies that should be adopted because it's the right thing for society, but nothing succeeds as well as economic gain.
Yes, indeed. If it's not profitable, it's not commercial, it doesn't go to scale.
Yeah, I can see a future where, you start putting Rondo batteries next to, major metropolitan areas and just store heat to heat the buildings and have it as a good backup.
Yes, indeed. We have a number of projects like that across Europe right now. Europe has more district heating systems than the U.S. New York is a great example of where there is a substantial district heating. And this is absolutely a place where the cogeneration fits beautifully, local clean energy supply from a safe energy storage unit that you could put in the basement of a building.
Yeah.
Because there's nothing to combust or spill or something. And it's also high energy density.
Well, John, this has been tremendously interesting to go back, a couple thousand years to the Hippocaust and, Roman baths, and you modernizing that technology to solve one of today's biggest industrial problems, I think is really exciting.
Thank you so much.
Thank you for listening to Good Clean Energy.